Good. Yep. All right. Does this make sense to you? Now you can find kernel pretty easily. This is the third example. Yep. So we can show that this kernel here you get a subset of kernel is a subset of where is that kernel? Here kernel is a subset of this vector space. We can show that this kernel is subspace, not only subset, it is a subspace of domain V, vector space V. Right? This is here kernel of a linear. This is very important. Linear, not transform. Linear of a linear transformation is a subspace of domain V, right? Because this is a linear transformation, this one is true. The zero element in domain V maps to zero element in W. We know that because this is linear. Why this is true? Because this is linear transformation. That's why, right? You remember, yeah. These are the properties of linear transformation. Zero element in V maps to zero element in W. All right, you know that. That means zero belongs to kernel of this transformation. That means kernel is non-empty. That is your first step, right? If you want to show some subset is a subspace, first you have to show non-empty. Yep. So you have to show that one is non-empty. This kernel set is non-empty. It has at least one element. All right. This is non-empty set. All right. Then take any two element in kernel. All right. So then show then take two element. How do you show a subset? Take any two elements in the kernel of T, right? T. You have to show U plus V also in kernel of T. All right, let's try to show this step, right? How do you show that? Let's consider the transformation of sum of U and V. And because this T is linear, you can split in this way, right? Because it is linear. The first condition, right? We can split this one in this way. U is an element in kernel of T. That means the U maps to zero element in W, right? Then this one is equal to zero element in W, right? Which is this. Because V is in kernel T, this one is equal to zero element in W. Zero, because this is zero element, 0 plus 0 is 0. Therefore, U plus V, when you transform U plus V, what do you get? Again, you get zero element. This maps to zero element in W. That means U plus V in this set kernel of T. Similarly, you can show this one in this set. Therefore, kernel of T is a subspace. Right? It is simple. All right. So here you have V, vector space V. This is W. This is your map from V, W. This is your transformation, which is linear. Linear means those two conditions are met, right? Linear, right? That so you can find the kernel. Kernel means all elements in kernel map to zero element in W, zero element in W. So it is called, this set is called kernel. So we showed that this subset is a subspace of V. This kernel subset, this kernel set is a subspace of V, right? Okay. Kernel is subspace. All right, what does it mean? Subspace here, if you look at this one, if you here look at this one. All right. So this is your transformation VW. All right. These are vector spaces. All right. Kernel is a subspace of this is V, this is W. Kernel is a subspace of V. This is 30, right? This is the map. This is your map, right? T. This is 30. 30. All right. So we show that this is a subspace of V. Okay, right. What does it mean? So if you write this transformation in matrix form, something like this here, something like, so X is an vector in W, right? So X is an element in W. Element means vector in W. No, not W, V. So if you write this transformation in matrix form in this way, A times X. So what does kernel means? If X belongs to kernel of T, if you write this transformation in matrix form like this, so so if this X in kernel of T, that means T of X should be equal to 0 element in W, right? So if you write this one in matrix form, look at this, see, AX. What is this? A times X is equal to 0. Basically, you are finding solutions to this homogeneous linear system. Kernel is, what does it mean? Kernel of T is the solution set of this homogeneous system. Kernel of T means is same with the solution set of this homogeneous system. AX equals 0. Right? So kernel of T is sometimes called the null space of T. Yep. I think you remember. So we have discussed earlier null space of A. So if you write T in matrix form, then so the null space of A is the solution space of this homogeneous system. I think you remember, right? Did you remember these things? We have discussed these things before. Did you remember? Just let me know. Otherwise, this would be difficult. Did you remember we found solutions to homogeneous system, right? If you write T in terms of matrices, then what do you get? A kernel means the solution space of AX equals 0, homogeneous system, linear system. All right. So sometimes that's why you call null space of T. Kernel of T is sometimes called null space. I think you remember we call the null space of A is the set of all solutions, right? I think you remember, right? Then okay. All right, here look at this. They have given the transformation in the form of matrices, right? Here, T. T is a linear transformation from this vector space to this one, and they have they have a represent. So this is represented by this matrix form, right? Okay, A is the matrix. X is in the domain, right? So find a basis for kernel of T. So if you write this transformation in matrices, basically, if you want to find kernel of T, if you want to find kernel of T, what do you want to find? So if you want to find kernel of T, so basically you find the solution space of this linear homogeneous system. So let's find solution space. Ax equals 0. I think we found. I think you have solved ton of exercises. I think have given a lot of exercises. You found solution space. I think now it is easy for you to compute, identify kernel of T, right? So how do you do that? How do you do that? Reduce this matrix to echelon form, right? If you want to consider the right hand side, you can consider, but you don't need to consider because all are 0. But if you have non-homogeneous, say this is B, then you have to consider this augmented matrix. I think you remember, right? So because this is 0, don't need to consider this one here because this is 0, right? Right? Okay, reduce this matrix to Gaussian echelon form. Bureau operations reduce this matrix to echelon form. Okay, here look at this. This is the now first we focus on the first row, and we find the first non-zero element in the first row. This one is the non-zero, first non-zero. Then this would be the pivot element, right, of row 1. So you don't need to consider the right hand side of this because this is all the time 0. When you do many operations, you get 0 all the time. But if you have B here, non-zero value, non-homogeneous, so you have to consider this augmented, right? Don't need to consider this, right? Okay, this is the pivot element. Then kick out this element under this pivot element. Kick out. You know how to kick out, right? You know how to vanish these elements. Do row operations, right? Then you can set 0 C under this pivot. Now you go to second. Now you can focus on the second row, and this is the non-zero one, and something like that. Do the same. Do the same. You know this thing. Okay. Yeah. All right. Now we analyze it. So now we analyze. So this is the reduced echelon form of A, right? Now you can find what was the question? Yeah, find the basis. All right. So now we consider Ax equals 0. Right. So this is your reduced one. We are dealing with reduced one. We don't deal with this one. This one is complicated. That's why we reduce that, right? all the time reduce the matrix using your operations and reduce to echelon form, right? Now, now you can find solutions to this linear system. This is the, I think you can, I think you are able to do this one, right? So you will get these two base elements. These are, I think these are linearly independent base elements of solution set of this homogeneous system. Therefore, when you span using these two vectors, you get the solution space of this homogeneous system. That would be the kernel of T. All right, that would be the kernel of T. So this is a yep. I think you understand, right? Did you understand this? I hope you understand pretty clearly, because we have done ton of questions on homogeneous, non-homogeneous. We found solutions to homogeneous. The set of all solutions of homogeneous system is called null space. Null space. That null space is same with the kernel of T. All right. So I hope makes sense. Any questions? If you want to ask. Let's move on here. Look at this here. Kernel is same with the solution space, null space. So T is a transformation from Rn to Rm, and T is defined by this. T is given in matrices form, right? In this way, right? Therefore, the kernel of this transformation is the null space of A. That means null space means solution space of this linear system, right? We have discussed that. All right, we know that, right? Okay, let's talk about the range of this transformation. So we only talk about the kernel. Kernel means kernel of this transformation. Kernel means, so kernel is a subset of V. So if you take any element in kernel, that maps to 0, 0 in W. That's it. If you pick any element in kernel, that maps to 0. That's the kernel. So the kernel is subspace of V, and if you write this linear transformation in matrix form, the kernel is the solution space of homogeneous system AX equals B, right? That is clear, I think. So I need your feedback. I don't know whether you understood or not. Did you understand what this kernel of T means? Did you understand? Kernel, if you write this transformation in if you represent this transformation in matrix form AX, so this is X in V. If you if you write this transformation in matrix form AX, right? Then the kernel is the solution space of this homogeneous system. So does that make sense to you? Do you have any questions? Yeah, there's a I'm saying again, Yep, that's that. Please give your feedback, right, to this. Please ask others to do this one. Do if you can give anything. If you don't like my lectures, just express that. Right? I don't like his lectures. I don't like to come. Right? Just give your feedback. We need your feedback. Right? Okay. All right. Let's move on. All right. All right. Now we are going to talk about range of transmission. Range. Yep. Range. Let's draw that. Uh-huh. Transformation means relationship between two vector spaces V and W. Right? Transformation. So this V is called domain. W is called codomain. If you consider this image, how do you range means if you consider all mapping from domain to codomain, so this one would be your range. So range, this is the image of V. This is called again a range. This is the image of V. This one is the image of V, right? Under this transformation. So again, we call this is range of T, right? Or image of V, right? Same thing. Range, you can call range or range of this transformation, which is image of this entire vector space, right? So we know that this is a subset of W. Now we can show this range is not only subset, it is a subspace of W. We are going to prove that if range of T is not only subset, but it is a subspace of W. That is the second theorem, the next theorem. Yeah. We know that kernel is a subset of the kernel. What is the image of kernel? Image of kernel is 0 element in W, right? So we showed that a kernel is we know that kernel is a subset of V. We showed that it is not a subset, it is a subspace of V, right? So how do you find? If you write this transformation in matrix form, how do you find the kernel? You can find the kernel by finding solution space of this homogeneous system. So if you find the solution space of this one, then you get this kernel of this transformation, right? Okay, now we go to range. So image of this entire vector space is called the range of T, range of transformation. So we know this is a subset of W. It is not only only a subset, but also a subspace. So we are going to show that. All right, let's show it is subspace. First, how do you show a subset is a subspace? First, you have to show it is non-empty. How do you show that? How do you show that? We know that this is a vector space. W is a vector space. 0 belongs to W, because it is a vector space, the additive identity. This is called additive identity, right? Zero element, right? In W, and we know that this is a linear map. This is a linear transformation. So if it is a linear transformation, what does it mean? What does it mean? So the zero element in V maps to zero element. Exactly maps to zero element in W. This one. Right? Right? Therefore, what? Therefore, right? Therefore, zero element in W belongs to range of T, because here there's a mapping. There's a mapping. So we grab the map. We grab the map. So T, we know that this is a linear transform, right? This T is a linear transform. So we have discussed the properties of linear transform here. Zero element in W maps to zero element in zero element in V maps to zero element in W, because this is a linear transformation. Because of that, zero belongs to range of T, right? V W. This is the image. So so this is a zero element in W, and we know that this is because this is linear. Zero element in V maps to zero element in W, then this should be in this set, right? This should be in this set. This belongs to range of this belongs to image of range of T. All right, therefore range is non-empty subset of W. Then how do you, then next step, pick any two elements in the range. Now you have to show the addition of these two elements belongs to the range of T. All right, because T is linear, right? T is linear. You can pull out T in this way because T is linear. Pull out T, transform T in front of, because T is a linear transform, right? Therefore, T U plus V equals TU plus TV. That means something like this. You have to visualize these things, right? Let's try to visualize. So, right, don't have space here. Let's try to visualize. All the time, draw a diagram, right? Okay, this is VW and transformation from here to there, T, and this is and if you consider entire V, you get, and this is the image of V. This is again we call this, we given, so how do you say, this is a range of T. You can say range of T or image of V, right? So zero element in W, right? So we know that T is linear, therefore zero element in V maps to zero element in W, therefore zero element in the range of V, range of T, right? And pick any two elements, then we can say range of T is non-empty. Then pick two n elements. Pick two n elements. T, U, and TW in range of T. I will denote in this way, right? Then let's add these up, right? We don't know if so. T of U is this, yeah. This is T of U. This is T of W. When you add these up, we don't know whether the resultant one comes to this one or goes outside of this set. We don't know. Let's check that one. Let's check. Let's add this up. Okay, let's check that whether the resultant one, addition of these two, come back to the same set or goes to outside. All right, let's check that. W. We know that T is a linear, right? So T is a linear one. Can now see your screen participant. I think you can see my screen, right? Can you see my screen?
Yes, sir.
Thank you. You're beautiful. Yep. All right. So T is a linear transform. So you can pull out this T. U plus W. All right. What does it mean? Yes. That means, all right, we found an element here. It is called U plus V. That maps to this. That maps to this sum. That means this guy belongs to range of T because we found a mapping. There's a map from this element to that. That means this, when you add these two elements, because we found an element in the domain, right? When you take the transform of this element, right? Because this belongs to range of T. Therefore, this guy belongs to range of T, right? Here, range of T, right? Did you understand that, right? Because this guy definitely here, this is an element in domain. Transformation of take transformation of this element. That means this guy in the range of T. That means the sum of these two is, because these two things are equal, therefore sum of these two elements in the range of T. The first condition is met. Similarly, you can show the second condition, right? Therefore, range also a subspace of W. Kernel is a subspace of V, range is subspace of W. All right, subspace of, kernel subspace of V, range of T is subspace of W. And the other thing here, last time I mentioned this one, right? If you write this transformation in matrix form like this, what do you get here? So something like this, right? So this is your first column, second column. How many columns are there? This is, let's see. So this is your x. X would be n dimensional. Here. X belongs to this vector space, and this should be n dimensional. There are n rows and one column, n rows, one column. Then this should be m plus n. Otherwise, this does not make sense. n equals, the dimensions should increase if you want to multiply these two matrices. We know that x is n dimension, x has n coordinates, right? So therefore, the dimension of x is n by 1. Then this, if you write this one in matrix form, then A is a matrix. A is an m by n matrix. Okay, all right. It is clear, right? I think it is clear to you, right? A is m by n matrix. All right, then. All right. So we have experience dealing with these AX, AX equals P. We have experience, right? We have discussed a lot of things. Okay, so this is column 1. How many columns are there? N number of columns, M number of rows. Column 1, column 2, up to column N. Right, N number of columns. All right, you can express or rewrite this one in terms of columns, right? So first one, let's say this is your first one, x1, x2, up to xn, right? C1 column times x1. x1 is a real number, right? Here, first coordinate of x, right? And C2 times x2, Cn times xn. So if you write this transformation in matrix form, right? So T of x means, so this is equal to T of x. This is equal to T of x. That means this transformation, this is the image of x, or image of x. Image of x is an element in the column space of A. So this is a linear combination of columns of A. So x is a general element in Rn, right? So this could be expressed in terms of columns of A. So therefore the range, so you can show the range is the column space of A. The range. So this is guys, range is a column space of A. Does it make sense? I think it makes sense. Oh, 38 students. I think we have only 38 students now. Oh my God. So, right. Yeah, number is reducing. So the range is the column space of A, right? So here, look at this. So this transformation is given in terms of matrices. A is given. X is an general element in R5, right? Then find the base for a range of T. How do you find that? Find the column space. Find the base of column space. Reduce this matrix to echelon form, row echelon form, and you can analyze the columns of that matrix, reduce echelon form. Let's analyze that. Okay, can do that. So this is the reduced echelon form. So let's analyze. All right, this these two are linearly independent. You cannot write this one in terms of this. Therefore, these two linearly independent. This could be right in terms of these two, right? This one 2 times this column plus minus 1 time this one. Therefore, this one is linearly. So you can write this one in terms of these two. Let's look at the other one. All right. Here 0, 0, 1, 0. This cannot be written in terms of these two. Therefore these three columns are linearly independent, because this one cannot be written in terms of these two, or this one cannot be written in terms of these two. Anything linearly independent, right? Look at this one. Okay, here you have number, another number in second coordinate, third. This could be written in terms of these three, right? These three, this one and this one and this one. Therefore, the column space, it has only 3 base elements. Now we compare. So if these 3 vectors are linearly independent, that means the corresponding columns are linearly independent, right? So this is the base. I think you can show, because we know we have discussed these things. So these three columns of A are linearly independent. Therefore, this is a basis for range of T. All right, that makes sense. Does that make sense to you? My God, we have another. All right. Yeah, it takes time. I think we have another 1 month. I think we have 1 month to cover everything, right? Yep. Yeah, we have time. I think. Yep. All right. Did you understand? This is a. Yep. Yeah. Yep. Let's go back to our schedule. The null space of transformation. Yep. And null theorem map today. Yep. Yep. Any questions? Yeah, this is a basis for range of T, right? The column space. So if you write this one in terms of matrices, then the column space of A would be the range of T, right? So remember that, right? So if you write this, you can write any transformation in matrix form. So you can write any transformation in matrix form. So AX. So in this way, X maps to AX. So what is this? So solution space. What is this one? So when you consider the set of all solutions to this homogeneous system, that set would be the kernel of T, another one, and column space of A would be the range of T, right? All right. Okay, rank of T, these are definition. If you have a linear transformation from V to W, right, rank of that transformation is the dimension of a range of T. So the rank of T is 1, 2, 3. because dimension is one. How many base elements? 1, 2, 3. So the dimension uh, of 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 range of T is 3. Therefore, rank of this transformation is 3. Right? And multi T, that means dimension of kernel T. Dimension of kernel T. So here, look at this. So I think you remember you express this transformation in matrix form. So the solution set of homogeneous system AX equals 0, homogeneous system would be your kernel T. So you can find that. So the dimension of this one is 2. The dimension of kernel T is 2. So which is equal to nullity T. These are definition nullity of transformation of T, right? Transformation T, right? These are the rank is the dimension of range of T. Nullity T is dimension of kernel of T. Okay. So yeah, written in terms of matrix, then rank of T is the rank of T is dimension of column space. Yeah, column space. That means the rank of T. I think you remember, right? You remember. We have discussion with that on 7A. Yep, here. Here. Row space, columns, and null space. Null space. I mean, these are very easy for you now, right? Matrices, you have learned a lot of matrices. Yep. Rank, yep. Remember rank of A. Here rank nullity A, nullity T, yep. Rank, yep. Here rank of A is dimension of column space or row space. Rank of A is the same with rank of T. Okay. Rank of A is same with rank of T. Rank of T is same with nullity A. Same thing, right? All right. This is very important. This is the theorem. Yeah, this theorem here, rank nullity theorem. Rank nullity theorem. Yeah. So you have a linear transform from V to W. V and W are vector spaces, right? And V is finite dimensional, yeah, n-dimensional vector space. So dimension of V, that means if you pick a basis for to pick a basis for V, it has n number of base elements, right? Linearly independent elements, right? N dimension, linear transform dimension V into a vector space W. Then rank of T plus nullity of T is equal to dimension of V, dimension of domain of T. This is dimension of domain of T. Nullity T means dimension of kernel of T. Rank of T means dimension of range of T. All right. Okay. I think, yep. There's that. Yeah, we have discussed this one. I think you remember here. So I think I don't. Yeah. So This one is true, right? So we have, I think under this one, I think we haven't discussed the proof of that one. I think yeah, we haven't discussed that because yep, that's okay. We can what's that? Yep. Yes. Mm-hmm. Yeah, I don't take time to do that one. Yep. So 957. Yep, 857. So this theorem is pretty important, right? So let's solve a couple of examples, right? Okay, let's discuss couple of examples. Okay, all right. So find the rank and nullity of this transformation defined by this. All right, they express this transformation in terms of matrices, right? So what is that? X in R3 maps into X. A is given. The A is given, right? Okay, so let's find the rank of T and nullity of T. So rank of T means rank of A, right? Rank of T means rank of, yep, rank of T means rank of A. Rank of A, rank of A means when you reduce this to echelon form, it is already echelon form. The rank of A, I think you remember non-zero rows, the number of non-zero rows of the rank of A. So, so there are two non-zero rows, then the rank of T is equal to 2. So when you represent this transformation in matrices, so nullity means what? What does it mean? Nullity. Solution dimension of solution space of this homogeneous system. Or you can use this theorem, right? Or you can use this theorem because you found nullity of T, no, rank of T. So the dimension of V is what? Dimension of V, the dimension of domain is 3. You found, you know, the rank of T, rank of T is 2. Then you can find, without finding solution space, you can use this theorem, nullity of T or dimension of kernel of T is equal to dimension of V minus dimension of rank T. Yeah. Rank, not dimension of range of T. So what is the dimension of domain of this transformation? 3, yep, 3 minus rank of T. Rank of T is 2. Therefore, the nullity T or dimension of kernel of T, that means the solution space of this linear system. That means this, I think, when you find the solution, let's find here. No, we don't have time, right? So when you find the solution, you get some one base element. I think something like this. Yeah, something like this. I don't know. You get something like this. That's why nullity T means dimension of kernel T, right? All right. So let's let's consider another one. All right, transformation between these two vector spaces. It is linear, very good. Find the dimension of kernel if the dimension of range of is 2. Okay, dimension of domain is 5. You know the dimension of range of T is 2. You can use this theorem, right? 5 domain is 5. Yeah, dimension of domain is 5 minus 5 minus 5 minus 2. Dimension of range, then you get the dimension of kernel. Yeah, 5 minus 2 is 3. And rank is what? A rank of T means a rank of A, right? If you write this transformation in matrix form, rank of A, rank of T, rank of rank of T, rank of T. If you have the nullity, the dimension of V is 5. Nullity is what? Nullity, kernel is 3. Yeah, 5 minus 3 is nullity is 4. Nullity is 3. Why is that? Rank 5 minus nullity 3. Nullity. Yeah, second one. Nullity is here. Find the rank of T. If the nullity of T is 4, yeah, we can do that. All right, I hope you understood this part, right? Second, stop recording.